Hello. Okay, everyone. So now let's spend the last few minutes of class talking about the first law of thermodynamics. So the first law of thermodynamics. So we'll learn about the first law here, and then you'll learn about the other laws of thermodynamics in Chem 401, where you talk about entropy and free energy of a system. We won't talk about those topics here. What we'll talk about here is enthalpy. Okay? So when we talk about the law of thermodynamics, it's a statement, it's a universal statement. There are no exceptions. So laws are usually no exceptions. Okay? So the law of thermodynamics are statements, where, it's a universal truth or validity. Okay, there are no exceptions to deny this truth. All right. So the first law of thermodynamics, it's pretty straightforward. Energy is conserved, or more, if we were to explain it a little bit more, the energy of the universe is constant. Okay, so the energy of the universe does not change. What happens is that forms of energy are being converted to different forms. So it's not like energy is being lost, it's just being converted to another form, so energy is constant. Okay, so let's talk, there'll be a lot of equations we go into, but for today, we're just going to touch upon some of them. Okay, so in this photo, energy is neither created nor destroyed. The energy absorbed, so this is a picture of an iced tea, okay? Lemon slice there. The energy absorbed by the system, the ice cubes, so we're saying, the ice cubes is absorbing the energy because it's at a lower temperature than the water, right? Or the tea. So it's going to be exactly equal to the energy lost by its surroundings, the tea. So the tea becomes cold, right? So the ice absorbs the heat, eventually it melts, and then eventually the tea will warm up. But we could represent this transfer of energy by saying the energy of the system is equal to the energy that was to the negative energy that came from the surroundings. So in this case, the energy of the ice absorbed energy from the tea, which is our surroundings. So our system here is ice, and then what's around the ice is our surroundings, and that's the tea. Okay. So the total energy before and after any process is carried out, it must be the same, right? So the total energy before and after must be the same. So when we say total energy, we mean the energy of everything that may be altered as a result of the process. So we usually call that the system. So the energy of everything in the system, the total energy, it must be the same before and after a process. Okay, so we could say the energy total before a process must be equal to the energy total after a process. Okay? So let's do an example here. What do we mean by that? Okay, so say I have this apparatus here. So I have a piston cylinder apparatus, and it's filled with an ideal gas, shown below. And you see the piston here is held to a constant volume, so it's going to hold the cylinder to a constant volume because we put some stops here that prevents the piston from moving. All right. So then we have this brick here is then brought into contact with the apparatus, and the brick is at a higher temperature than the gas in the piston cylinder apparatus. So as a result of this, the average kinetic energy, right, of the particles in the brick is going to be larger because it's at a higher temperature, right? Because we know that a higher temperature means your average kinetic energy is larger. So in this case, it'll be larger for the brick than of the molecules of the gas, right? So we can say temperature of the brick is greater than the temperature of the gas. And thus, we can say kinetic energy of the brick is going to be greater. It's going to be greater than the kinetic energy of the gas. Okay? All right. So what happens? How does the energy get transferred? So some of the kinetic energy of the brick particles is transferred to the wall of the container, and then eventually, through collisions with the wall, to the gas, to the molecules of the gas. Okay? So as a result of this, the temperature of the gas, right? The temperature of the gas gradually increases. And so the motion, what happens is the motion of the gas will then, of the gas molecules, increases. And then collisions then we say, then collisions of the gas molecules with the walls of the container become both more frequent, right? There's going to be more of them, and more forceful, right? And so the pressure in the container will then increase. Okay, so that's how we kind of describe what's happening when we bring a hot object in contact with a cold object. All right, so in other words, you know, all the energy of the brick loses, all the energy the brick loses is gained by the gas and the piston cylinder apparatus. So what we can say is negative Q brick equals Q gas. So eventually all that heat will be transferred to the gas particles. And assuming that no energy is lost to the surroundings, that will always be the case, but most often than not, that will probably not be that will probably not happen unless the container is completely insulated. Okay. All right. So let's just talk about one more thing, and then we'll probably stop there for today. So in this experiment, the gas is the system, is our system, and the brick and cylinder apparatus are the surroundings. Because what we care about is the system we're studying, right? So usually the cylinder or beaker or flask is how we contain our system, so we can study it. So and everything else outside of our system is the surroundings. Okay. So now let's start talking about building a set of equations that kind of represents the reality of what's happening as the system comes to, thermal equilibrium. So we're going to consider the total energy in this experiment as the sum of the energy of the system and its surroundings, right? So we want to think about the energy total. So E total equals energy of the system plus energy of the surroundings. Okay, so Sir and Sis will be system and surroundings, respectively. And now we can actually change this to reflect our system. So we can say the gas in the apparatus is our system. So we can write E total equals E gas, energy of the gas, plus energy of our surroundings. Okay? Now, okay. So let's stop there for today. So I don't want to go past too much time because that'll be too much information. We'll pick up where we left off next week in lecture 14. Okay, so that'll be it for this lecture, or introduction to thermochemistry and how energy changes, how we can measure energy changes between our system and surroundings. So I'll see everyone in the next lecture. Okay, bye-bye.